For decades, we were taught a comforting number. The universe is about 14 billion light-years across. Big, yes, but finite, understandable, almost tidy. Then a telescope looked into what appeared to be empty darkness and quietly proved that number wrong. Not slightly wrong, catastrophically wrong. The universe we can observe is not 14 billion light-years wide. It is closer to 93 billion light-years across, a scale so vast it breaks the mental shortcuts we rely on to make sense of reality. This wasn't discovered by theory or speculation, but by observation. The James Webb Space Telescope stared into a region of sky that once looked nearly blank and uncovered hundreds of thousands of galaxies hiding in the dark. Some formed when the universe was barely getting started. Galaxies that are too massive, too bright, too structured to exist so early. Black holes that grew far faster than physics says they should. Cosmic structures spanning millions of light-years when there wasn't enough time for gravity to build them. These findings don't just add new details to our cosmic story. They challenge the foundation of what we thought we understood about size, age, and growth itself. This video is not about what we've learned. It's about what we got wrong and how a deeper look into the darkness forced us to rethink the true scale of everything. To understand why these discoveries are so unsettling, you have to accept one simple fact that changes everything. Seeing far away is the same as seeing into the past. Light does not arrive instantly. It moves at a fixed speed, and that speed turns distance into a time machine. Look at something a mile away, and you're seeing it as it was a few microseconds ago. Look at the moon, and you're seeing light that left its surface about 1 second earlier. When you look at the sun, you see it as it existed 8 minutes in the past. These delays are small, but they grow rapidly. The nearest star beyond our sun appears as it was over 4 years ago. Every step outward pushes you deeper into history. This means the night sky is not a snapshot of the present. It is a layered archive of moments scattered across time. James Webb takes this idea to its extreme. It was built to detect light that began its journey when the universe itself was young. As space expands, it stretches light along with it. Visible light emitted by ancient stars gets pulled into longer, redder wavelengths during its journey. This effect, known as redshift, transforms ultraviolet and visible light into infrared by the time it reaches us. Webb is designed to see this stretched light. It doesn't just look farther than previous telescopes. It looks earlier. When Webb detects a distant galaxy, it is capturing photons that left their source billions of years ago, long before Earth existed, before our sun formed, before the Milky Way had finished assembling. To grasp how early this is, compress the entire age of the universe into a single calendar year. The Big Bang happens at midnight on January 1st. Our sun doesn't appear until early September. Earth forms days later. All of human history unfolds in the final seconds before midnight on December 31st. The galaxies Webb is seeing formed in the first days of January. Their light has been traveling almost the entire lifetime of existence to reach us. Every image Webb sends back is not just distant, it is ancient. And by reading that ancient light, we begin to understand just how much of the universe's story was hidden from us until now. When one of these ancient photons finally reaches the James Webb Space Telescope, its journey is almost beyond comprehension. It began traveling toward us more than 13 billion years ago, at a time when the universe was still in its infancy. Long before galaxies like our own had taken shape, before Earth existed, before even the raw materials for life were present. That single particle of light was released from a newborn star. For nearly the entire history of the cosmos, it crossed expanding space without rest, without deviation, carrying with it a record of the moment it was born. And when it finally arrives, Webb does not rush the process. To capture these signals, the telescope often stares at the same tiny patch of sky for hours at a time, sometimes collecting light for nearly 10 hours just to build a single image. The contrast is staggering. Photons that traveled for billions of years are gathered slowly and deliberately, one by one, until they form a picture we can analyze. But seeing a faint smudge is not enough. To understand how far away an object truly is, scientists break that ancient light apart using a technique called spectroscopy. By spreading the light into its component colors, they can identify precise patterns that act like fingerprints for different elements. Those patterns are shifted toward longer wavelengths, depending on how much the universe expanded while the light was in transit. The greater the shift, the farther back in time the light originated. This is how distances are confirmed, not guessed. Through these measurements, Webb doesn't just show us distant objects, it timestamps them. Every image becomes a verified snapshot from a specific era in cosmic history. In this sense, Webb is not taking photographs in the ordinary way. It is excavating. Each frame is a fossil, a preserved moment from the universe's deep past, locked inside light and finally uncovered after billions of years of silent travel. As Webb began returning its deepest images, scientists expected to see faint, primitive smudges, the cosmic equivalent of rough sketches, not finished structures. Instead, they found something deeply unsettling. Among the discoveries was a galaxy catalogued with an unremarkable name that hid an extraordinary reality, Jade's GS Z14-0. Its light began its journey when the universe was only a few 100 million years old, barely out of cosmic infancy. Yet what Webb revealed was not a fragile, barely assembled object. It was bright. It was compact, but substantial. And it was far more developed than anything that should have existed so soon. According to every standard model of cosmology, galaxies at that age should have been small, dim, and chaotic. Collections of gas just beginning to form stars. This one wasn't. It shone with an intensity that suggested hundreds of millions of stellar masses already in place. That alone was alarming. But the deeper scientists looked, the worse the problem became. Spectral analysis showed signatures of elements heavier than hydrogen and helium, carbon, oxygen, nitrogen. These elements are forged inside stars and spread through space only when stars live and die. Their presence meant that at least one earlier generation of stars had already formed, burned, and exploded before this galaxy even appeared. The timeline began collapsing in on itself. Gravity is not fast. Gas does not instantly condense into stars. Dark matter halos take time to accumulate mass. Star formation unfolds over millions of years, and chemical enrichment takes even longer. Yet here was a galaxy that seemed to have skipped steps. It was as if someone had uncovered a smartphone buried beneath the streets of ancient Rome. The technology wasn't just advanced, it was out of place. And Jade's GS Z14-0 was not alone. Webb found others like it, galaxies from the same era that were too large, too bright, too organized to exist according to the rules we thought governed cosmic growth. Together, they pointed to a growing crisis. The early universe was producing far more light, far more structure, far more complexity than theory allowed. Astronomers began calling it the too much, too early problem. Models predicted scarcity. Webb revealed abundance. Predictions said the first 500 million years should be a slow climb from darkness. Observations showed a universe already bustling with activity. Researchers double-checked everything. Instruments were calibrated. Data was reanalyzed. Independent teams verified the results. The measurements held. The galaxies were real. Their distances were confirmed. Their properties could not be waved away as errors. This forced an uncomfortable conclusion. Either star formation was far more efficient in the early universe than we understand, or some fundamental assumptions about how matter behaves under extreme conditions are incomplete. Perhaps gas collapsed faster in a denser cosmos. Perhaps dark matter assembled structures more aggressively. Perhaps unknown physical processes briefly dominated the universe's youth. Whatever the explanation, it was clear that the standard story, smooth beginnings followed by gradual complexity, was missing something essential. The universe did not ease into existence. It surged. And these impossible galaxies were the first clear signs that our neat, orderly timeline was an illusion built from limited vision. Webb didn't just extend our view deeper into space. It exposed a period of cosmic history that refuses to behave the way it's supposed to. The earliest chapters of the universe are not quiet or tentative. They are loud, crowded, and shockingly productive. And once that realization sets in, a far more disturbing question follows. If galaxies this massive and this mature existed so early, what else formed before we were ready to see it? The deeper Webb forced us to rethink early galaxies, the more another problem came into focus, one that makes those discoveries even stranger. If the universe is only 13.8 billion years old, then logic says light should not have traveled farther than 13.8 billion light-years. Simple distance equals speed times time. Yet when astronomers calculate how far away the most distant observable regions actually are today, they arrive at a very different number. The edge of the observable universe is not 13 or even 20 billion light-years away. It sits roughly 46.5 billion light-years in every direction, forming a sphere more than 90 billion light-years across. At first glance, this sounds impossible. Nothing can move faster than light, so how can anything be farther away than light has had time to travel? The answer lies in understanding that space itself is not static. It stretches. A useful analogy is dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they are crawling across the surface, but because the surface between them is expanding. The dots aren't moving through space. Space is growing beneath them. The universe works the same way. Galaxies are not racing through space away from us at impossible speeds. The space between galaxies is expanding, carrying them apart. Another way to picture this is a treadmill. Imagine light running toward us at full speed, while the treadmill beneath it slowly accelerates in the opposite direction. The light keeps moving forward, but the distance it must cross keeps increasing. Early in the universe, distant galaxies were much closer when they emitted their light. Over billions of years, cosmic expansion stretched the space between us and them. So by the time that ancient light finally arrives, the source is now vastly farther away than where it began. This leads to the idea of the cosmic horizon. There is a boundary beyond which light has not yet had time to reach us since the beginning of the universe. Everything inside that boundary is observable in principle. Everything beyond it is causally disconnected. Those regions exist, but no signal from them can ever reach us because the expansion of space outpaces the ability of light to cross the gap. What makes this even more unsettling is that the expansion of the universe is not slowing down. It is speeding up. Observations show that some unknown force, called dark energy, dominates the cosmos. Unlike matter, dark energy does not dilute as space expands. As more space comes into existence, more dark energy comes with it, pushing expansion faster and faster. This acceleration means that over time, more galaxies will slip beyond the cosmic horizon, disappearing forever from view. Even galaxies we can see today will eventually fade, their light stretched into invisibility as space carries them away faster than photons can travel. Distance, then, is not just a measure of space. It is a measure of time, expansion, and limitation. The universe is not a fixed arena with objects placed inside it. It is a dynamic system where the stage itself is growing, reshaping what can be seen, what can be known, and what can ever be reached. Once the nature of cosmic expansion is understood, the scale of what Webb uncovered becomes even more staggering. To test how crowded the universe truly is, astronomers pointed the telescope toward a region of sky so small it appears insignificant, a patch only slightly larger than 3 full moons held at arm's length. To human eyes, and even to earlier telescopes, much of this area looked nearly empty. Webb stared anyway, and it did not glance. It watched. For a total of 250 hours, the telescope remained locked on this single region, patiently collecting ancient infrared light photon by photon. What emerged from that long exposure shattered every expectation. When the Hubble Space Telescope examined this same region years earlier, it identified roughly 10,000 galaxies. That number already seemed impressive. Webb's image revealed something else entirely. Nearly 800,000 galaxies filled the frame, not clusters piled on top of each other, but distinct separate systems scattered across cosmic time. The error wasn't subtle. It wasn't a small correction. The earlier census was wrong by a factor of almost 80. Where Hubble saw islands, Webb revealed a continent. And this wasn't random chaos. The galaxies were not sprinkled evenly like static on a screen. They followed a pattern. Dense intersections where galaxies crowded together. Long, faint threads stretching between them. Vast, empty regions where almost nothing existed at all. This was the cosmic web, the large-scale structure of the universe made visible in unprecedented detail. Dark matter forms invisible filaments that stretch across millions of light years, guiding normal matter as it flows under gravity. Where filaments intersect, galaxies accumulate, forming groups and clusters. Between these threads lie cosmic voids, enormous regions of emptiness where matter never gathered. Webb didn't just confirm this structure. It exposed it in motion across nearly the entire history of the universe. The reason Hubble missed so much of this comes down to wavelength. Hubble was optimized for visible and ultraviolet light, the same narrow band human eyes evolved to see. That works well for nearby galaxies whose light hasn't been heavily altered by expansion. But the most distant galaxies emit light that has been stretched far beyond visibility. Their ultraviolet and blue light arrives as infrared. To Hubble, they were effectively invisible, not because they were too faint, but because they existed in a different part of the spectrum. Webb was designed specifically to see this hidden universe. Its infrared detectors pierce through cosmic dust that blocks visible light. They capture photons stretched by expansion over billions of years. Regions that once looked like black voids suddenly ignited with structure. Entire populations of galaxies appeared where nothing seemed to exist. And Webb didn't stop at imaging. Every detected galaxy was measured. Distances were calculated. Brightness was cataloged. Mass estimates were derived. Star formation rates were inferred. The result was one of the most detailed astronomical data sets ever assembled. Then something remarkable happened. Instead of locking this information behind institutional walls, scientists released it to the public. Images, measurements, catalogs, interactive maps, everything made accessible. Anyone, anywhere, could explore this deep field, search for objects, trace structures, and test ideas. This democratization of data transformed a single observation into a global resource. Researchers across the world began mining the same information, checking conclusions, finding patterns, uncovering new anomalies. The legitimacy of the discovery didn't rest on one team or one telescope. It was reinforced by transparency and repetition. And with every reanalysis, the conclusion held. The universe is far more crowded than we believed, not just at the present day, but deep into its past. What looked empty was full. What seemed sparse was dense. What appeared simple revealed structure layered on structure. Webb didn't merely add more galaxies to the count. It forced a re-evaluation of how matter organizes itself on the largest scales. The cosmos is not a quiet expanse dotted with occasional islands of stars. It is a vast, interconnected network, woven from dark matter, illuminated by galaxies, and shaped by expansion itself. And once you see that web in its full extent, it becomes impossible to believe that our earlier picture was ever complete. As the cosmos Webb field data spread through the scientific community, one pattern stood out above all others, and it was deeply troubling. The early universe was far brighter than it had any right to be. When astronomers added up the total light coming from galaxies in the first few 100 million years after the Big Bang, the numbers refused to cooperate. According to standard cosmological models, the universe at that stage should have been dim, sparse, and inefficient at producing stars. Matter had only recently cooled. Gravity was still gathering material. The machinery required to turn gas into stars was supposed to be slow and limited. Yet Webb's observations showed something very different. Depending on the epoch examined, the total brightness of the early universe exceeded predictions by factors of 2, 5, even 10. This was not a subtle discrepancy buried in statistical noise. It was a glaring mismatch between theory and reality. Entire populations of galaxies were producing enormous amounts of light far too soon. The phrase began circulating quietly at first, then more openly. Too much light, too early. Scientists did what they always do when confronted with an apparent contradiction. They searched for mundane explanations. Perhaps these galaxies were not as massive as they appeared. Bright objects can deceive. A small galaxy filled with unusually hot, young stars can outshine a much larger one filled with older stars. So researchers reanalyzed stellar populations, adjusted mass estimates, and recalculated star formation rates. The discrepancy shrank slightly, but it did not disappear. Next came black holes. Supermassive black holes feeding on surrounding gas can shine with the combined brightness of billions of stars. If many early galaxies hosted actively feeding black holes, known as active galactic nuclei, their light could inflate brightness measurements. This explanation worked in some cases. A handful of galaxies were reclassified once black hole contributions were accounted for. Their apparent masses dropped. Their defiance softened. But again, the solution was incomplete. Even after removing the most extreme black hole-driven systems, the early universe was still producing far more light than models allowed. Then came the galaxies that refused to be tamed at all. Objects so massive, so luminous, so mature, that even generous corrections could not reconcile them with existing theory. astronomers began referring to them informally as universe breakers. Not because they literally broke the universe, but because they seemed to break the rules we thought governed it. These galaxies existed within the first 400 to 500 million years, yet they contained stellar masses that should have required billions of years to assemble. Some appeared to be 10 times more massive than anything that should have existed at that age. Their stars were already organized. Their gas had already been processed. Their light suggested sustained star formation over extended periods, not brief flashes. Time was the enemy here. Every step of galaxy formation has a minimum pace enforced by physics. Gas must cool before it collapses. Cooling takes time. Collapsing clouds fragment into stars over millions of years. Massive stars live fast and die young, enriching their surroundings with heavy elements only after exploding. Dark matter halos grow hierarchically, merging slowly into larger structures. None of these processes can be rushed arbitrarily without violating known physical limits. Yet the observations demanded acceleration. Somehow, the early universe was converting raw material into stars with extraordinary efficiency. Somehow, it was building massive systems in a fraction of the expected time. As more deep field surveys were completed, the problem worsened rather than improving. Different regions of the sky showed the same pattern. Different instruments confirmed the same excess brightness. This was not a fluke of one observation or one data set. It was a systemic issue. The early universe was not behaving like a younger version of the modern cosmos. It was operating under a different regime entirely. The implications were unsettling. If galaxies formed earlier and faster than expected, then their influence on the surrounding universe must also have begun earlier. They would have flooded space with radiation sooner. They would have ionized hydrogen gas earlier. They would have seeded heavy elements faster. The entire timeline of cosmic evolution, from rionization to structure formation, would need revision. Textbook chapters built on gradualism suddenly looked incomplete. This forced theorists into uncomfortable territory. Some proposed that star formation itself worked differently in the early universe. Perhaps the first galaxies were far better at converting gas into stars, wasting little material. A denser cosmos could mean more frequent cloud collisions, triggering rapid collapse. Others suggested the initial mass function might have been skewed toward massive stars, which burn brighter and faster, boosting total luminosity without requiring as many stars overall. Another avenue focused on dark matter. Different dark matter properties could alter how quickly halos form and how efficiently they draw in gas. If dark matter clumped more aggressively in the early universe, it could provide deeper gravitational wells sooner, accelerating galaxy growth. There were also hints that continuous streams of cold gas might have flowed along cosmic Webb filaments directly into young galaxies, replenishing fuel faster than stars could consume it. Each idea helped a little. None solved the problem completely. What made the situation especially difficult was that the standard cosmological model still worked extraordinarily well in many other areas. It accurately predicted the cosmic microwave background. It matched large-scale structure statistics. It explained elemental abundances with precision. This was not a failed theory. It was an incomplete one. The early universe appeared to be exposing its blind spots. The phrase "new physics" began appearing more frequently, not as a declaration, but as a possibility. Perhaps unknown processes dominated the universe's youth and faded later. Perhaps assumptions that hold today break down under primordial conditions. Webb had not overthrown cosmology, but it had cornered it. The data demanded explanation, and familiar tools were no longer sufficient. What emerged from this growing tension was a realization that the universe did not gradually wake from darkness. It ignited. The first few 100 million years were not a quiet prologue. They were a burst of activity, light, and structure that reshaped everything that followed. The early cosmos was not tentative. It was efficient, aggressive, and astonishingly productive. And if that was true, then the story of how everything began was far more dramatic and far less understood than we ever imagined. As troubling as the early galaxies were, they came with an even more disturbing companion hidden at their centers. Many of these young systems appeared to be powered by supermassive black holes that should not have existed yet. Some weighed millions, others billions of times the mass of our Sun, already fully active when the universe was only a few 100 million years old. This created a problem that went beyond galaxies and struck at the heart of fundamental physics. Black holes do not appear fully formed. They grow, and that growth is limited by strict physical laws. In the conventional picture, black holes begin as the remnants of massive stars. Even the largest stellar collapse produces a black hole only tens of times the mass of the Sun. From there, growth happens gradually as surrounding gas falls inward. But accretion cannot proceed arbitrarily fast. As matter spirals toward a black hole, it heats up and releases energy. That radiation pushes back against incoming material, creating a natural speed limit known as the Eddington limit. Even under ideal conditions, growing a stellar mass black hole into a billion solar mass giant should take billions of years. Webb was finding them in less than 500 million. This was not a small timing error. It was an existential contradiction. Astronomers confirmed the signatures carefully. Spectra revealed dense, rapidly rotating gas disks. Emission lines showed extreme temperatures and velocities. These were not hypothetical objects. They were actively feeding black holes, already dominating their host galaxies. The question was unavoidable. How did they grow so large so fast? Several explanations emerged, each more radical than the last. One idea involved dark stars, hypothetical objects powered not by nuclear fusion, but by dark matter annihilation. In the early universe, dark matter densities may have been high enough to sustain these stars, allowing them to grow to enormous sizes, thousands or even millions of solar masses, before collapsing directly into massive black holes. Such a head start would bypass the slow, early stages of growth. Another possibility was direct collapse. Under special conditions, entire clouds of gas might have collapsed straight into black holes without forming stars at all. If a cloud containing 100,000 solar masses avoided fragmentation, it could produce a black hole of comparable mass in a single event. This process has never been observed directly, but simulations show it is theoretically possible under the extreme conditions of the early universe. A third explanation relied on violence. The young cosmos was smaller and denser. Galaxies were closer together. Collisions were frequent. If black holes merged repeatedly in rapid succession, their masses could build faster than accretion alone would allow. Gravitational wave detectors have confirmed that black hole mergers occur today. There is no reason to think they were rare in the past. Perhaps early black holes grew through relentless merging, assembling their mass through cosmic traffic accidents. None of these explanations fully solves the problem on its own, but together they suggest that black hole formation in the early universe followed pathways that no longer operate today. What makes this more than a curiosity is the role black holes play in shaping everything around them. A supermassive black hole is not just a passive object. As it feeds, it releases enormous amounts of energy. Jets of particles blast outward at near light speed. Radiation heats surrounding gas. This feedback can trigger bursts of star formation or shut it down entirely by driving gas away. In this way, black holes act as regulators of galaxy growth. Finding them so early means they influenced cosmic evolution almost from the beginning. They helped to determine how galaxies formed, how fast stars were born, and how matter was distributed across space. The micro and the macro became inseparable. A single object smaller than our solar system could dictate the fate of an entire galaxy. Webb's discoveries suggest that black holes were not latecomers riding along with galaxy growth. They were architects. Their presence may explain why early galaxies appear so bright, so massive, so evolved. But this explanation comes at a cost. It implies that our understanding of gravity, matter, and energy under extreme conditions is incomplete. The universe built its largest monsters before we thought it was capable of doing so. And if black holes could grow this fast, regulate this early, and shape structure on such short timescales, then the early universe was not just active. It was aggressively efficient. The same tension that plagued galaxy formation now extended inward, down to the smallest and densest objects imaginable. The universe was not waiting patiently for complexity to emerge. It was forcing it into existence at every scale, all at once. To understand how black holes could gain such a head start, scientists were forced to look even further back, beyond galaxies, beyond black holes themselves, to the very first stars. Webb provided a clue, not through images, but through chemistry. In the spectrum of several extremely distant galaxies, researchers noticed something deeply unusual. The balance of elements was wrong. Nitrogen appeared in quantities far higher than expected, especially when compared to oxygen. This ratio does not occur naturally in ordinary stellar populations. Normal stars do not produce nitrogen in such excess. Supernova explosions cannot account for it either. But theoretical models had predicted exactly this chemical signature from a type of object that had never been observed directly before. Primordial monster stars, the first generation of stars to ever ignite. These stars, known as Population 3, formed from a universe that contained almost nothing but hydrogen and helium. No carbon, no oxygen, no metals of any kind. In modern star formation, heavy elements help gas cool efficiently, allowing clouds to fragment into many smaller stars. The early universe lacked those cooling agents. Without them, gas clouds collapse differently. Instead of breaking apart, they continued collapsing inward, feeding a single growing object. The result was a star unlike anything that exists today. These primordial stars may have reached masses hundreds, thousands, even tens of thousands of times greater than our Sun. They burned ferociously hot, pouring out radiation at staggering rates. Their lives were short, measured in a few million years at most. But during that brief existence, they changed everything. Inside their cores, nuclear reactions ran at extremes modern stars never reach. Helium fused into carbon, then carbon rapidly captured more helium nuclei through what is known as the carbon-nitrogen-oxygen cycle, producing enormous quantities of nitrogen. When these stars died, they did not explode in familiar supernovae. Many collapsed directly into massive black holes, skipping the explosion entirely. Others shed nitrogen-rich material into surrounding space through powerful stellar winds before collapsing. This ejected material mixed with nearby gas, leaving behind a chemical fingerprint that Webb can still detect billions of years later. The anomalous nitrogen ratios seen in distant galaxies are that fingerprint. They are the fossil remains of stars that lived and died at the dawn of time. This discovery does more than confirm a long-standing prediction. It provides a missing link. Monster stars offer a natural pathway to early supermassive black holes. If a star begins life already thousands of times the mass of the Sun, its collapse creates a black hole with an enormous head start. Instead of growing from stellar remnants of a few dozen solar masses, these black holes would begin their existence already massive, capable of reaching supermassive scales far faster than standard growth allows. Monster stars also help explain another major mystery: reionization. After the Big Bang, the universe cooled into a fog of neutral hydrogen that absorbed light. For hundreds of millions of years, space was opaque. Something had to flood the universe with enough high-energy radiation to strip electrons from hydrogen atoms, making space transparent again. Ordinary stars struggle to do this efficiently. Monster stars do not. Their intense ultraviolet radiation would have torn through hydrogen across vast regions, reionizing the universe rapidly and early. In doing so, they transformed the cosmos from darkness into light. But their influence does not stop there. These first stars were also the universe's first factories of complexity. Every element heavier than helium had to be forged inside a star. Carbon, oxygen, nitrogen, silicon, iron, all of it began in stellar cores. Monster stars produced these elements faster and in greater quantities than later generations could. When they died, they seeded the cosmos with the raw materials needed for planets, chemistry, and eventually life. Without them, the universe would remain simple, sterile, and dark. Our own existence traces back to these objects. The oxygen you breathe, the carbon in your cells, the iron in your blood were all manufactured inside stars. Long before the Sun formed, long before Earth existed, those elements were scattered through space by stellar deaths. Our star formed from gas enriched by countless previous generations. We are not separate from the early universe. We are made from it. Webb's detection of population 3 fingerprints turns abstract theory into tangible ancestry. It shows that complexity did not emerge slowly and reluctantly. It arrived early, violently, and efficiently. The universe's first stars were not gentle lights flickering into existence. They were cosmic beacons, blazing briefly, reshaping their surroundings, and leaving behind legacies that echo across billions of years. Through them, the early universe became capable of building galaxies, feeding black holes, clearing cosmic fog, and forging the elements that make thought possible. In revealing their chemical ghosts, Webb has connected the most distant reaches of space to the most intimate facts of our own biology. The story of the cosmos is not just about where matter went. It is about how matter learned to become complex enough to wonder where it came from. Once the first stars ignited, seeded space with heavy elements, and collapsed into black holes, gravity finally had the raw material it needed to sculpt the universe on its largest scales. What emerged was not a random scattering of galaxies, but a vast architecture that spans hundreds of millions of light years. Matter did not distribute itself evenly. It flowed. Invisible rivers of dark matter formed first, tracing out a skeletal framework long before galaxies became visible. Ordinary matter followed these gravitational contours, falling into elongated filaments that stretched across space like cosmic highways. Where multiple filaments intersected, matter piled up, forming dense nodes that would become galaxy groups and clusters. Between these structures, matter drained away, leaving behind enormous voids, regions so empty they contain only a fraction of the average cosmic density. This interconnected network is known as the cosmic web, and Webb has revealed it not as a static diagram, but as a living structure evolving across time. One of the most striking discoveries within this framework is an early structure nicknamed the cosmic vine. Webb identified a chain of tightly packed galaxies stretching more than 10 million light-years across space when the universe was only a few billion years old. At that stage, such large, coherent structures were not expected to exist. Yet there it was, dozens of galaxies aligned along a filament, already behaving like a mature system in the process of becoming a massive cluster. Compared to our own Milky Way, which spans roughly 100,000 light-years, the cosmic vine is colossal. It represents gravity operating efficiently and early, pulling matter together faster than models predicted. These early structures are not isolated curiosities. Webb has cataloged thousands of galaxy groups and protoclusters across cosmic history, allowing astronomers to trace how structure builds step by step. In the earliest epochs, galaxy groups appear chaotic. Their members are irregular in shape, rich in gas, and forming stars at furious rates. Interactions are frequent. Mergers are common. As time progresses, these groups begin to settle. Gravity tightens their bonds. Gas heats up. Star formation slows. Galaxies transition from turbulent, star-forming systems into smoother, more organized shapes. Spiral arms stabilize. Elliptical galaxies emerge from the aftermath of collisions. Eventually, many groups merge into larger clusters, becoming the most massive gravitationally bound objects in existence. Webb's infrared sensitivity allows this entire process to be observed continuously rather than inferred from isolated snapshots. Previous surveys could only glimpse certain stages. Webb connects them into a coherent timeline. It shows how dark matter halos grow, merge, and deepen over billions of years, drawing in galaxies along filaments like beads sliding toward a knot. It reveals how environment shapes destiny. Galaxies embedded in dense regions evolve differently from those drifting alone in the cosmic field. In clusters, galaxies are stripped of gas by hot plasma, shutting down star formation. In isolation, they continue forming stars for longer periods. The cosmic web is not just a map of where matter is, it is a map of how galaxies live and die. Void regions tell a complementary story. These vast expanses, sometimes hundreds of millions of light-years across, represent places where gravity lost the competition early. Slightly underdense regions in the young universe gradually emptied as matter flowed outward toward filaments and nodes. Over time, voids expanded, growing emptier and larger as structure condensed elsewhere. Standing inside a void would mean seeing almost nothing in any direction for tens of millions of light-years. Yet even these empty regions are part of the Webb's evolution. Their growth helps drive the sharpening contrast between dense filaments and empty space. Webb's observations confirm that the universe's large-scale structure did not emerge slowly and uniformly. It assembled rapidly, guided by dark matter and accelerated by the same efficiency that produced early galaxies, black holes, and monster stars. The web formed early, thickened quickly, and continued refining itself over cosmic time. Every galaxy we observe today resides somewhere within this network, connected indirectly to every other through chains of gravity. Our own galaxy sits on a modest filament linking larger clusters, part of a structure so vast that light from some regions began its journey toward us when dinosaurs still walked on Earth. What Webb reveals is not just a picture of where things are, but a demonstration that the universe is organized on scales far beyond intuition. The cosmic web is the universe's blueprint, drawn by gravity, written in dark matter, and illuminated by galaxies. It shows that complexity did not emerge randomly or late. It was embedded into the fabric of the cosmos from the beginning, unfolding across billions of years into the immense, structured universe we see today. As intricate and crowded as the cosmic web appears along its filaments, its structure is defined just as much by what is missing as by what is present. Between the luminous threads and dense clusters lie vast regions where gravity failed to gather matter at all. These are cosmic voids, the universe's great expanses of emptiness, and they are not accidents or gaps in our observations. They are the inverse imprint of gravity itself. In the early universe, matter was distributed almost uniformly, but not perfectly. Some regions were slightly denser than average, others slightly less. Gravity amplified these tiny differences. Dense regions pulled matter inward and grew denser still. Underdense regions lost matter as it flowed outward toward filaments and nodes. Over billions of years, those depleted regions became voids, growing larger and emptier as structure elsewhere became richer and more complex. Today, the largest voids stretch hundreds of millions of light years across, making them the biggest continuous structures in the universe, even though they contain almost nothing. A typical void holds less than 10% of the average cosmic matter density. Some contain far less. If you could stand at the center of one, the night sky would be nearly black. The nearest galaxy might lie tens of millions of light years away in every direction. These regions matter because they are simple. In dense environments, galaxies move under the combined influence of cosmic expansion and local gravitational pulls from neighboring structures. Their motions are messy and difficult to interpret. Voids strip that complexity away. Galaxies inside voids experience minimal gravitational interference. Their motion is dominated almost entirely by the expansion of space itself. This makes voids ideal laboratories for cosmology. By studying how galaxies drift within and away from voids, scientists can measure how fast the universe is expanding and how that expansion changes over time. Voids are especially sensitive to dark energy. As dark energy accelerates expansion, voids grow faster than dense regions. Their boundaries move outward as matter evacuates toward filaments. The size, number, and distribution of voids therefore encode information about the properties of dark energy and the behavior of gravity on the largest scales. Webb's observations, combined with other surveys, show that void statistics align closely with predictions from the standard cosmological model. This agreement is reassuring, but it also sharpens the tension created by early galaxies and black holes. On the largest scales, the universe behaves exactly as expected. On smaller scales and earlier times, it does not. The emptiness of voids also highlights an unsettling truth about our place in the cosmos. Most of the universe's volume is empty. Galaxies, stars, and planets occupy thin threads and isolated nodes embedded in a vast sea of nothingness. The luminous universe we focus on is a minority feature. Emptiness dominates. This has observational consequences. Light traveling through voids experiences less gravitational distortion than light passing through dense regions. It follows cleaner paths, preserving information about distant sources more faithfully. At the same time, voids stretch with expansion, lengthening the journey photons must take. In some cases, light can spend billions of years crossing a single void, carrying with it a record of expansion unperturbed by local structure. Voids also reveal how extreme the universe's contrasts have become. Gravity did not gently rearrange matter into a smooth gradient. It created stark divisions, crowded filaments filled with galaxies on one side, near total emptiness on the other. This contrast continues to sharpen as expansion proceeds. Dark energy accelerates the separation, making voids emptier and filaments thinner relative to the growing volume of space. Over cosmic time, the universe becomes more structured and more empty at the same time. Philosophically, voids force a pause. They remind us that structure is not the default state of the universe. It is the exception. Complexity exists because gravity overcame expansion locally, not because matter naturally prefers to clump. In most places, gravity lost. If conditions had been only slightly different, the universe might consist almost entirely of diffuse gas and darkness, with no galaxies at all. Instead, we inhabit one of the rare regions where matter gathered enough to ignite stars, build planets, and produce observers capable of contemplating emptiness itself. Webb's view of voids does not diminish the universe's grandeur. It deepens it. The contrast between nothing and something, between vast silence and intricate structure, is part of what gives the cosmos its scale and meaning. The voids are not blank spaces in an otherwise interesting picture. They are essential components of the universe's architecture, shaping how everything else evolves. In their emptiness, they offer clarity, a reminder that the story of the universe is not only about accumulation and growth, but also about absence, separation, and the relentless stretching of space that continues to carry everything farther apart. Understanding the emptiness of cosmic voids brings us back to the messenger that makes all of this visible in the first place: light itself. Everything Webb reveals depends on how light behaves as it crosses an expanding universe. When light leaves a distant galaxy, it does not travel through a fixed stage. Space stretches while the light is in motion, pulling its wavelength longer and longer. This stretching shifts light toward the red end of the spectrum, a phenomenon known as redshift. The farther the light travels and the longer it journeys through expanding space, the more extreme that shift becomes. In the early universe, young stars emitted intense ultraviolet and visible light. By the time those photons arrive here billions of years later, their wavelengths have been stretched many times over. Ultraviolet becomes visible. Visible becomes infrared. Push the distance far enough, and every trace of original starlight slides completely out of the range human eyes can detect. This is why infrared is not optional for studying the early universe. It is inevitable. The most ancient galaxies are not faint because they are weak. They are faint because their light has been diluted and stretched across space and time. Earlier telescopes like Hubble were revolutionary, but they were limited by design. Hubble was optimized for visible and ultraviolet wavelengths, the narrow window our biology happens to use. It could detect some near-infrared light, but not with the sensitivity needed to see galaxies at extreme redshifts. To Hubble, many early galaxies were effectively invisible. Their light arrived at wavelengths its instruments could barely register, buried beneath noise or completely beyond reach. This invisibility created a false impression of emptiness. It wasn't that galaxies weren't there. We simply weren't looking with the right eyes. Webb was built to solve exactly this problem. Its instruments are tuned to infrared wavelengths ranging from just beyond visible light to deep infrared. This allows it to capture photons that have been stretched by factors of 10, 15, even 20 since their emission. To do this, Webb had to be engineered in a radically different way. Infrared light is easily overwhelmed by heat. Any warm object glows in infrared, including the telescope itself. Webb therefore operates at temperatures near absolute zero. A massive multi-layer sun shield blocks heat from the Sun, Earth, and Moon, keeping the instruments cold enough to detect signals that are barely distinguishable from nothing. Its mirror, coated in gold to maximize infrared reflection, is far larger than Hubble's, allowing it to collect more light from extremely faint sources. Webb's location, far from Earth, reduces thermal interference and stray radiation. Every aspect of its design serves a single purpose: to see what cosmic expansion has hidden. When Webb observes a distant galaxy, it is not peering through darkness by chance. It is reading the universe in the language expansion has written. Redshift dictates where ancient light appears. Infrared reveals what visible light conceals. The discoveries Webb has made were not lucky accidents. They were the unavoidable result of finally matching our instruments to the reality of an expanding universe. Once we built a telescope capable of seeing stretched light, the early cosmos could no longer stay hidden. Webb did not change the universe. It changed our ability to perceive it. And once that perception shifted, the universe revealed itself as older, larger, denser, and more complex than we had ever allowed ourselves to imagine. Once Webb proved it could see the universe exactly as expansion demands, it was inevitable that it would be asked a more dangerous question. Not how far the universe stretches, but how fast it is stretching right now. For nearly a century, astronomers have known that space is expanding. Measure the distance to a galaxy, measure how redshifted its light is, and you can calculate how fast it is moving away. The proportionality between distance and recession speed is called the Hubble constant. In principle, it should be a single number describing the universe today. In practice, it has become one of the deepest crises in modern cosmology. There are two main ways to measure the expansion rate. One looks backward, using the earliest light in the universe, the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature fluctuations in this radiation encode information about the universe when it was only 380,000 years old. From that data, scientists can infer how fast the universe should be expanding now. That method produces a value around 67 kilometers per second per megaparsec. The second method looks locally, measuring distances to nearby galaxies using well-understood objects like Cepheid variable stars and type Ia supernovae, whose intrinsic brightness is known. Compare how bright they appear to how bright they should be, and you get their distance. Combine that with redshift, and you get an expansion rate closer to 73. The difference may sound small. It is not. The gap is statistically significant and persistent. It refuses to disappear no matter how carefully the measurements are repeated. For years, scientists suspected systematic errors. Perhaps dust affected brightness. Perhaps distance ladders were miscalibrated. Perhaps early universe assumptions were flawed. Webb was expected to help resolve this by acting as an independent referee. With its infrared vision, Webb could measure distances to supernova-hosting galaxies with less interference from dust and with unprecedented precision. If the problem came from earlier instruments, Webb would expose it. Instead, Webb did the opposite. It confirmed the local measurements. Using multiple independent techniques, Webb's results matched Hubble's value, not the early universe prediction. The tension did not weaken. It hardened. This outcome was unsettling because both sides of the measurement now appear robust. The early universe data fits the standard cosmological model beautifully. The late universe data, confirmed by Webb, is equally consistent. They cannot both be right unless something fundamental is missing. One possibility is that dark energy is not constant. In the standard model, Dark energy behaves like a cosmological constant, exerting the same influence throughout cosmic history. But if dark energy evolved over time, growing stronger or weaker, it could cause the expansion rate to change in ways the early universe cannot predict. Another possibility is new physics affecting how light travels through space, subtly altering redshift measurements over vast distances. Others speculate about unknown particles, extra fields, or modifications to gravity itself. None of these ideas are confirmed. All of them would represent profound changes to our understanding of reality. The Hubble tension is not a technical annoyance. It affects everything: the age of the universe, its size, its ultimate fate. If we cannot agree on how fast space is expanding today, then our cosmic story contains a hidden chapter we have not yet read. Webb did not solve this problem. It made it impossible to ignore. By confirming the discrepancy instead of erasing it, Webb pushed cosmology to the edge of its comfort zone. Either the universe is more complicated than our best model allows, or we are missing a fundamental ingredient that governs expansion itself. In both cases, the implications are enormous. The universe has already shown us that it grew structures too early, built black holes too fast, and produced too much light too soon. Now it is telling us that even its expansion does not follow the simple rules we expected. The picture is still coherent, but it is no longer complete. And history suggests that when precise measurements refuse to agree, nature is preparing to reveal something entirely new. As debates about expansion and dark energy intensified, Webb delivered something rare in cosmology: a quiet confirmation rather than a new contradiction. For decades, dark matter had been the unseen architect behind every large-scale structure we observe. Its existence was inferred from galaxy rotations, gravitational effects, and simulations, but direct evidence of its distribution on the smallest cosmic scales remained elusive. The cosmic web was predicted to be built on filaments of dark matter, thin strands connecting massive halos like tendons in a vast skeletal system. Theory said they were there. Webb helped show that they truly are. By exploiting a subtle effect known as gravitational lensing, astronomers used Webb to detect the influence of dark matter along filaments between galaxies. When light from a distant background galaxy passes through a region filled with mass, its path is slightly bent. The distortion is tiny, almost imperceptible for individual galaxies. But when thousands of such distortions are analyzed together, a pattern emerges. Webb's sensitivity allowed these minute deflections to be measured with unprecedented precision, revealing mass where no luminous matter existed. The results matched predictions strikingly well. Dark matter was not confined to halos around galaxies. It stretched between them, forming continuous bridges that traced the same filaments seen in galaxy distributions. This was the invisible framework holding the cosmic web together. For the first time, these filaments were not just theoretical lines on a simulation or inferred from galaxy positions. Their gravitational imprint was directly observed. This achievement matters because it anchors the universe's structure in something real and measurable. The same dark matter that guided early galaxy formation, fed black holes, and shaped clusters is responsible for the web's integrity. Without it, ordinary matter would never have clumped efficiently enough to form the structures Webb observes. Seeing dark matter on filaments also strengthens confidence in the broader cosmological picture at a time when other aspects are under strain. While expansion rates and early galaxy formation raise questions, the behavior of dark matter across scales continues to align with theoretical expectations. The skeleton holds, even as the flesh grows stranger. Webb's lensing measurements do not reveal what dark matter is made of, but they remove doubt about its role. The universe is not just illuminated by galaxies. It is structured by something we cannot see, yet whose presence is written into the paths of light itself. In revealing this invisible scaffolding, Webb provided a rare moment of closure. Amid growing mysteries, it confirmed that at least one of the universe's deepest predictions was correct. The cosmos truly is woven around an unseen framework, a dark skeleton supporting everything that shines. With the universe's invisible skeleton finally brought into view, attention returned to a question that now felt unavoidable. Just how many galaxies are there, really? For decades, the accepted estimate hovered around a few 100 billion galaxies in the observable universe. That number already sounded extravagant, safely beyond everyday intuition. Webb quietly made it inadequate. When astronomers combined the deep field results with models of cosmic structure, the implications were staggering. If a tiny patch of sky could hide hundreds of thousands of galaxies, then scaling that density across the full observable volume pushes the total far beyond earlier guesses. Not billions, possibly trillions. And not as a speculative upper bound, but as a plausible revision driven by direct observation. Many of these galaxies are small, faint, and ancient. Their light stretched nearly to invisibility by expansion. They were never truly absent. They were simply hidden. Each additional galaxy is not just a point of light. It is a system of stars, many with planets, many with the raw ingredients for chemistry. Even if only a fraction host environment suitable for life, the sheer increase in numbers transforms the scale of possibility. Worlds that once seemed rare become statistically inevitable. The universe shifts from being vast to being almost overwhelmingly fertile. This realization carries an emotional weight that numbers alone cannot capture. Humanity's long struggle to place itself at the center of existence collapses under the enormity of the count. We are not living in a universe sparsely decorated with islands of light. We are living in one saturated with them, layered across time, most forever beyond reach. Our galaxy is not special in number or position. It is one participant in a network so extensive that no single viewpoint can grasp it all. Webb's contribution here is subtle but profound. It does not show us every galaxy. It shows us enough to force humility. The realization that most of the universe's contents will never be seen, never be visited, and never interact with us reshapes the meaning of cosmic perspective. We exist in a small pocket of a much larger reality, defined not by privilege, but by circumstance. And yet, there is something quietly extraordinary about this moment. We are alive at a time when the universe is still visible, when its ancient light can still reach us before expansion carries it away. Trillions of galaxies may exist, but only a fraction are accessible to observation, and that fraction is shrinking. The fact that we can count it all, that we can infer structures beyond imagination, is a temporary gift. In recognizing how small we are, we also recognize how rare our vantage point is. Cosmic humility does not diminish meaning. It sharpens it. Once the scale of the galaxy population expanded, another question became impossible to avoid. If there were so many galaxies so early, how were they forming their stars at such astonishing rates? Modern galaxies like the Milky Way are relatively conservative. They convert only a small fraction of their gas into stars each year. Most of the raw material remains diffuse, cycling slowly through molecular clouds over billions of years. The early universe behaved nothing like this. Webb's observations show young galaxies turning gas into stars with an efficiency that dwarfs anything seen today. In some cases, these systems were forming stars 10 times faster than comparable galaxies in the modern cosmos. This was not a gradual acceleration. It was a fundamentally different mode of operation. The conditions of the early universe help explain part of the story. Space was denser. Galaxies were closer together. Gas was abundant and cold relative to the background radiation. Under these conditions, gravity had an easier time overwhelming pressure and turbulence. Streams of gas flowed along dark matter filaments directly into galaxy cores, delivering fresh fuel continuously rather than intermittently. Instead of waiting for internal processes to recycle material, early galaxies were fed by the cosmic web itself. Mergers also played a major role. Collisions between young galaxies were far more frequent, compressing gas and triggering bursts of star formation. Each encounter acted like a spark, igniting new waves of stellar birth. But even accounting for these factors, models still struggle to reproduce the observed efficiencies. Simulations can be tuned to increase star formation, but doing so often breaks agreement with other well-established observations. The universe seems to have balanced on a narrow edge, achieving rapid growth without tearing itself apart. This persistent mismatch reinforces a central theme. Observation is leading theory, not the other way around. Webb has revealed a universe that does not politely conform to our expectations. It formed stars earlier, faster, and more efficiently than our best models predicted. The early cosmos was not simply a scaled-down version of today's universe. It operated under different rules, with different dominant processes, and possibly with physics that no longer plays a major role. Every line of evidence points to the same conclusion. The universe's youth was an era of extremes, and understanding it requires letting go of assumptions built from studying the calm, mature cosmos we inhabit now. As the early universe reveals itself to be more intense and efficient than we imagined, attention inevitably turns forward in time, toward what now dominates everything: dark energy. In the universe's youth, matter ruled. Gravity pulled gas into stars, stars into galaxies, galaxies into clusters. Expansion existed, but it was slowing, restrained by mass. Over time, as space expanded and matter diluted, another influence quietly took over. Dark energy, whatever its true nature may be, does not thin out as the universe grows. Its density remains nearly constant. As more space comes into existence, more dark energy comes with it. Eventually, it surpassed matter as the dominant driver of cosmic behavior. That transition marked a turning point. Expansion stopped slowing and began accelerating. Today, dark energy shapes the future far more than gravity does. This acceleration has profound consequences. Galaxies beyond our local group are already receding faster and faster. Given enough time, most will cross the cosmic horizon, their light stretched beyond detectability. The universe will not end in darkness because stars burn out, but because expansion isolates everything. In one possible future, dark energy remains constant, and the universe drifts toward a cold, dilute state, known as heat death. In a more extreme scenario, dark energy grows stronger with time. Expansion accelerates without bound. First, galaxy clusters are torn apart. Then galaxies themselves unravel. Eventually, stars, planets, and even atomic structures are ripped apart as space expands faster than any force can resist. This hypothetical ending is known as the Big Rip. Whether it will happen is unknown, but its possibility underscores how little we truly understand about the force shaping our destiny. Dark energy is not just a cosmological parameter. It is the clock driving the universe toward its end. Time itself becomes strange when viewed across cosmic distances. Because light takes time to travel, every observation is a look into the past. Nearby galaxies appear almost as they are now. Distant galaxies appear as they were billions of years ago. The observable universe is therefore not a single moment frozen in space, but a layered structure of time. The farther we look, the deeper into history we peer. Webb's images are not just pictures of distant objects. They are cross-sections through time itself. A single deep-field image contains galaxies at many different ages, coexisting in the same frame, but separated by billions of years of history. This creates a profound distortion of intuition. There is no universal now that spans the cosmos. What we experience as the present is local. Elsewhere, the universe is younger or older, depending on distance. Time dilation compounds this effect. As space expands and gravity warps space-time, clocks tick differently in different regions. Light climbing out of gravitational wells loses energy. Time passes more slowly near massive objects. Over cosmic scales, these effects accumulate, subtly reshaping the flow of history. The universe is not evolving in lockstep. It is unfolding asynchronously, with different regions experiencing different cosmic eras simultaneously from our perspective. The observable universe is therefore a shrinking archive. There are regions whose light will reach us in the future, revealing epochs we have not yet seen. And there are regions whose light will never arrive, forever sealed beyond the horizon. Expansion is not just moving objects apart. It is erasing access to information. The universe is gradually hiding its own past and future. This makes our moment cosmically unusual. We exist at a time when the universe is old enough to be structured, rich with galaxies and stars, but young enough that much of it is still visible. Billions of years from now, observers, if any remain, will see a far emptier sky. The cosmic web will fade. Other galaxies will vanish from view. The universe will appear smaller, quieter, more lonely. The grand architecture Webb reveals today will be inaccessible. In that sense, time is not just something that happens within the universe. It is something the universe actively sculpts. Expansion defines what can be seen, what can be known, and what can be remembered. The early universe burned with intensity, forging structure at astonishing speed. The late universe drifts toward isolation, driven by a force we barely comprehend. Between those extremes lies a brief window where complexity, observation, and understanding are possible. Webb's greatest gift may not be the images themselves, but the realization that we are witnesses at a fleeting moment in cosmic history. The universe has a past filled with violent creativity and a future dominated by silent expansion. We stand at the intersection, looking backward across billions of years and forward into an accelerating unknown. Time, stretched by expansion and layered by distance, turns the universe into both a memory and a forecast. And for a short while, we are here to read it. After confronting the universe's past and future, it becomes clear that this transformation in understanding did not come from replacing one telescope with another, but from expanding the way we see. Hubble and Webb are often framed as rivals, but their relationship is closer to a relay. Hubble showed us the universe in the wavelengths most familiar to human senses. Its images defined modern astronomy. Spiral galaxies in sharp relief, nebulae glowing in visible light, deep fields that hinted at unimaginable distance. But Hubble was bound by the same limitation as our eyes. It saw primarily in visible and ultraviolet light, a narrow slice of reality shaped by biology, not by cosmology. Webb was built to look beyond that slice. Side by side, the difference is striking. Where Hubble shows sparse fields punctuated by a few faint galaxies, Webb reveals dense populations hidden in plain sight. Where Hubble sees darkness, Webb sees structure. This is not because Hubble failed, but because the universe changed the light before it reached us. Expansion stretched ancient starlight out of visibility. Dust obscured star-forming regions. Entire eras of cosmic history shifted into wavelengths Hubble was never designed to capture. Webb steps into that missing range. It does not invalidate Hubble's discoveries. It completes them. Together, they form a continuous story across wavelengths and time. Hubble excels at studying nearby galaxies, stellar evolution, and energetic phenomena in the modern universe. Webb extends that reach backward, unveiling the formative stages Hubble could only hint at. The contrast exposes a deeper truth about perception itself. Reality does not privilege the wavelengths we evolved to see. Most of the universe is invisible without instruments tuned beyond our senses. Infrared, radio, X-ray, gamma ray. Each reveals a different aspect of the same cosmos. Webb's impact comes from aligning technology with the physics of expansion. Once we looked where the universe had moved its light, the invisible became unavoidable. The early galaxies, the dense cosmic web, the excess brightness, all were always there. We simply lacked the means to see them. This continuity matters. Scientific progress does not discard what came before. It reframes it. Hubble gave us the first deep look. Webb shows us what that look was missing. Together, they demonstrate that understanding the universe is not about sharper eyes alone, but about learning where and how to look. Seeing more of the universe also means recognizing the limits of what can ever be reached. As Webb expands our view, it simultaneously sharpens a more sobering truth. Most of the universe is not just far away, it is permanently inaccessible. This boundary is known as the cosmic horizon, and it is not a physical wall or an edge in space. It is a limit defined by time, expansion, and the finite speed of light. Light can only travel so fast, and space itself is stretching faster with every passing moment. Beyond a certain distance, expansion wins. Signals emitted there will never reach us, no matter how long we wait. Those regions are not merely distant, they are causally disconnected. This horizon is observer-dependent. An observer in another galaxy would see a different portion of the universe, centered on their own location, with its own horizon. There is no privileged viewpoint from which the entire universe can be seen. Each observer carries their own bubble of visibility through space-time. This means that while the universe as a whole may be vast beyond comprehension, any single civilization is confined to a shrinking fraction of it. Even galaxies we can observe today are slowly slipping away. As dark energy accelerates expansion, their light becomes increasingly redshifted, stretched into wavelengths too long to detect. Eventually, they will cross the horizon and vanish, not because they cease to exist, but because the universe carried them beyond communication. This imposes absolute limits. No signal we send can outrun expansion beyond a certain distance. No message, no probe, no future technology can bridge that gap. The universe enforces isolation at the largest scales. This has implications not just for exploration, but for meaning. We often imagine a universe teeming with life, civilizations scattered across countless galaxies. Webb's discoveries make that scenario statistically plausible, even likely. But the cosmic horizon makes it irrelevant in practice. Most of those civilizations, if they exist, are forever beyond contact. They live in regions whose light will never touch ours. Even within our own observable bubble, the window for communication is limited. As time goes on, the number of galaxies available for interaction dwindles. The universe grows quieter. This cosmic loneliness is not emotional speculation. It is a consequence of physics. Expansion does not care about curiosity, intelligence, or intent. It separates regardless. The irony is sharp. The universe is more crowded than we imagined, yet more isolating than we hoped. Trillions of galaxies may exist, but only a tiny fraction can ever influence us. This reframes our place in the cosmos. We are not at the center, but neither are we connected to most of what exists. We are confined to a small island of space-time, drifting in an ocean that grows wider every second. Even knowledge is time-bound. There are events occurring right now beyond our horizon, whose existence we will never know. Entire histories unfold without ever leaving an imprint on our sky. The universe is not obligated to be observable. It simply is. Webb's revelations make this tension unavoidable. By revealing how much exists, it highlights how much is lost to expansion. The cosmic horizon is not just a boundary of space, but a boundary of possibility. It defines the maximum extent of shared history. Beyond it, the universe becomes a collection of separate realities, each evolving alone. This isolation is not tragic in a human sense, but it is profound. It reminds us that understanding is local, temporary, and fragile. We exist during a brief era when the universe is still readable, when light from distant epochs can still arrive, when the cosmic story is not yet fragmented beyond reconstruction. In the far future, observers may see a dark, empty sky, unaware that galaxies once filled it. They may infer expansion without ever seeing its evidence. In that future, the universe will appear smaller, simpler, and more lonely than it truly is. Our moment is different. We stand at a time when the horizon still contains enough information to tell a rich story. The cosmic loneliness we face is balanced by a fleeting privilege, the ability to know that we are not alone in existence, even if we are alone in experience. Reaching the edge of what can be seen forces a final adjustment in perspective. For most of human history, we placed ourselves at the center by default. The Earth felt central. The Sun felt special. Our galaxy felt unique. Each expansion of knowledge quietly dismantled those assumptions, and Webb completes that process with calm finality. Humanity is not central. We are not early, not late, not privileged by position. We are average observers living in an unremarkable galaxy on a typical filament of a cosmic web that extends beyond intuition. Trillions of galaxies erase any lingering sense of cosmic favoritism. There is nothing in the universe arranged for us. And yet, there is nothing that excludes us either. We are made of the same matter, governed by the same laws, shaped by the same processes that built stars, galaxies, and black holes. That realization does not diminish meaning. It reframes it. Meaning does not come from being central. It comes from being aware. The universe does not owe us comprehension, but for a brief window, it allows it. We exist during a rare era when the cosmos is both old enough to be richly structured and young enough to remain visible. The light from ancient galaxies has not yet been stretched beyond detection. The cosmic web has not yet faded into darkness. Expansion has not yet erased the evidence of everything that came before. This balance will not last. In the far future, observers may look out and see a sparse sky, unaware that trillions of galaxies once filled it. They may never know the universe's true scale. We do. Not because we are special, but because we arrived at the right moment. Webb's images are quiet reminders of that luck. They do not shout significance. They whisper humility. They show a universe that is vast, indifferent, creative, and fleetingly knowable. We are small within it, but not irrelevant. The atoms that make us were forged in ancient stars. The laws that govern our thoughts are the same laws that shape cosmic structure. When we look outward, the universe is not separate from us. It is our origin story, written across space and time. There is no final revelation waiting beyond this, no central truth that places us above the rest. There is only the ongoing act of seeing, understanding, and accepting our place. Gratitude emerges naturally from that acceptance. Gratitude that we live in an era when the universe still reveals itself. Gratitude that curiosity can reach across billions of years. Gratitude that for a moment, on a small planet around an ordinary star, the universe has become aware of itself. And then, quietly, the story continues, carrying everything farther apart, leaving behind images, measurements, and a fleeting understanding that once we were here, and we looked out, and we saw.